Megalodon ROV!
We're a 15-member company from San Mateo, California. We're based in Aragon High School, and this is our second year competing in the Meta ROV competition. We're extremely excited to be here. My name is Ben. I am the CEO of Megalodon ROV. This is Grendel, our lead mechanical engineer, Evan, our co-lead mechanical engineer, Zen, our float engineer, Aiden, our safety officer, Emily, our mechanical engineer, and Trisha, also a mechanical engineer. Here we have Valerie, our chief operations officer, Sani, our lead programming officer, Sarah, a programming engineer, Alex, a programming engineer, Jochi, a programming engineer, Martin, a programming engineer, and Hannah, a programming engineer. I will now pass it off to Valerie to discuss a little bit of an overview about our team.
Hi there. So, our company has recognized that it is no secret that the effects of climate change have been worsening, severely impacting the ocean temperature and acidity. As such, our company has created an ROV that is capable of various tasks that are crucial to the preservation of marine environments and species, whether that be the northern red-bellied dace or coral reefs. Our company also recognizes the interconnectedness of our planet and understand that saving the oceans not only means protecting millions of organisms, but also preserving the Earth as a whole. So now a little introduction into our ROV. Our ROV uses a 6-stressor layout in order to move in the water. Mounted on the frame are a 3D printed claw, as you'll see here, a watertight housing, and multiple cameras. I will now pass it back to Ben to talk about our company structure.
Our company is divided into 2 sections, the mechanical section as well as the programming section. Our team uses a work backwards mentality in order to manage our day-to-day tasks. What that means is we define our end goals first and set sub-goals going backwards. We've worked for over 2,000 combined hours on this ROV, and we're extremely excited to present it to you today. I will now hand it off to Evan to discuss our frame.
Our frame uses 12 1-inch PVCs connected by 3-way connectors to create a basis of our frame. Each frame, as you can see here, is pinned in place with a screw-in pin to make sure the pipes don't rotate when we are moving. Mechanisms are mounted using a 3D printed mounting system, which are secured by a strip of polycarbonate, which is inserted into an indent and then clamped down by hose clamps. This makes it a very modular frame and makes replacements and additions to our frame very simple. When adding and replacing parts, it is very important to keep in mind the buoyancy. In the beginning of our testing process, our buoyancy was severely unbalanced, and our ROV would constantly tilt when trying to move. To counteract this issue, we load our center of mass using a system of weights and ballast and a buoyancy foam. Down here, there's PVC pipes filled with sand to add weight to the bottom and lower our center of mass, and then we added PVC ballasts here that are sealed and buoyancy foam to further lower our center of mass. This allowed us to have simple and easy movement within the water. Next, I'll pass it on to Emily to talk about the watertight housing.
During last year's competition, our watertight housing flooded, causing all of our electronics to get damaged. Although various factors were put into why the electronics were damaged, mostly it was because of the floor epoxy job and the holes not being precise. This year, we decided to use a polycase enclosure due to its lower cost compared to commercially sold ROV enclosures. Using a drill press, we drilled into our housing in order to run potted and wetling penetrators, and to ensure that our enclosure had a watertight seal on land before putting any electronics into the water. We used this handheld vacuum, and ASOB water solution. I will pass it off to Grendel to talk about our claw.
So here is our claw. Our claw features a cross-shaped design in order to grab PVC pipes that are both horizontal and vertically oriented. This allows us to do our teleop phase more time efficiently, as we don't have to worry about tilting the robot. Additionally, we opted for a pneumatic system because in the beginning of the year, as we were trying to figure out how to, as we stated earlier, learn how to properly waterproof our enclosure, we used pneumatics so that we could kind of test and use our claw in parallel. Now I will be passing it off to Trisha to talk about it.
The tether is an integral component of our ROV. It contains 2 Cat6 Ethernet cables for transmitting camera feed and we also have 12 gauge wires for delivering power to the ROV and a pair of pneumatics for operating the claw. We also run all our cables through string leaf glands, which are on a piece of polycarb on the top of the ROV, which help prevent any damage from water pressure, environmental factors, and stress and pulling from our ROV. Now I'll be passing it on to Ben to talk about our electrical system.
Our electrical system is divided into two parts that are nearly independent of each other, with the exception of shared power distribution boards. First, we have our control system, and second, we have our camera system. Our control system starts on land, where we have a laptop connected to a controller, which then connects to a Cat6 Ethernet cable through a USB to Cat6 adapter. That allows us to send control signals from the controller and laptop to the ROV. Inside this watertight enclosure, we have an Arduino Mega that then sends the signals it receives from on land onto our electronic speed controllers, which then control our thrusters. As for our cameras, we use a system of balins which convert the analog signals into a signal that can be sent into the Ethernet cable. It is received on land, put through Ethernet to balun adapters, and the balins finally feed into AHD to HDMI connectors. The HDMI signal is fed into a laptop, which then displays the video feed. I will now be passing it on to Sandy to talk about our propulsion system.
So our ROV uses a 6 T200 thruster propulsion system. As you can see, 4 of the thrusters are attached to 4 vertical PVC pipes and are angled 45 degrees inwards to allow us to crab and move back and forth. And 2 of our thrusters are placed front and back, responsible for the depth control movement and the pitch forwards and backwards movement. This year, our ROV has achieved 5 degrees of freedom, including crabbing and diagonal motion, compared to last year's where we only had 4 degrees of freedom. I will now be passing it back to Ben.
Awesome. I will be discussing a little bit about our camera system. Our camera system this year includes 3 cameras, 2 of which are visible here. One faces the claw to allow us to easily complete tasks that utilize the claw, and one forward-facing camera that allows us to navigate our ROV. Within our watertight enclosure, right about here, there is another camera that faces down. I can put this up. We have a downward-facing camera located right there. This allows us to complete the transect line, which is on the bottom of the pool. I will now be passing it off to Grendel to discuss lasers.
So for our lasers, we are using them to properly measure the diameters of the 3D model. The laser system, as you can see here, it utilizes a foam shroud, which when underwater, the foam would go up, uncovering the lasers, and then when out of water, gravity pulls it back down, and then it would go back to covering. Last year, we used single point lasers as our first attempt because that's what we had seen online, but that did not work out for us. So this year, we opted for a cross-shaped laser. That way we could make parallel lines, which would also not only make it easier for us to make sure that the lines are parallel, but also make it easier for the programming side to get our measurements. Now I will be passing it off to Zen to talk about our build versus buy.
So first and foremost, our company would like to thank our parents and sponsors for monetary support, Aragon High School for allowing us to use their workshop, and Highlands Rec Center for allowing us to use their pool. And however, despite these amazing accesses to resources, we still like to maintain our mindset of remaining cost efficient. What this means is using PVC pipes or 3D printed parts, etc. Anything that we could do to avoid utilizing off-the-shelf products, we do. And we'll continue to.
I'm gonna talk about buying versus reusing. For our ROV, we use our T200 thrusters and our shroud right here. And to determine the reusability of parts, we looked at 2 factors: the cost of the part to buy new and the functionality of the part. From last year, the thrusters were still functional and are fairly expensive to buy, and so to reduce the amount that we spent on pre-assembled products and to reduce further waste, we used these thrusters. Here, we bought new PVC pipes and connectors because they were relatively cheap and relatively hard to reuse. Although we did reuse some parts, we made sure to prepare them differently to provide adequate challenge to our new members. Next, I'll be passing off to Aiden to discuss our safety procedures.
Okay, so our company strives to have a safe environment. We know that we benefit from mutual trust between each other. We have thruster guards which prevent foreign objects from entering the thrusters and causing any damage. We also have thruster shrouds that cover the lasers that prevent the laser from accidentally hitting something. We also have strain relief, which prevents the wire from having too much stress and getting ripped out. We also know that we benefit from creating limits and boundaries between each other, as we know that causing someone to pushing someone out of what they are comfortable with can cause them to accidentally do something that they are not too well known about, and that causes issues, and they will end up doing something that they would not like to be doing. I'll now pass it on to the programming team.
Alright, so now to explain our programming. So our programming team is split into 3 sub-teams. We have our navigation sub-team, our image processing sub-team, and our GUI sub-team. So on the navigation process, that communicates with the onboard Arduino Mega through a Pi serial library and also through the Arduino serial port. And then the camera data is fed into our image processing software through Ethernet. I'm gonna pass it on to Sani to talk about our manual control.
So our Python program parses the controller inputs, which include joystick and button statuses, and it converts these numbers to the 6 thruster PWM values, which are then sent to the Arduino through serial communication. And there they are parsed and processed again. But before the PWM values can be sent to the thrusters, we fine-tune them through our new PID algorithms, which I will pass on to Joshi to talk more about.
To further the navigational side, an emphasis was placed on satisfactory bot movement, and thus the PID system was born. And so the PID system, what it tries to achieve is maintain the bot's orientation for both roll and pitch, and also preserving the depth of the robot. And so additionally, a bigger controller was used as it provides more precise readings and more functionality.
So a little bit about image processing. For image processing programs, we use Python and relied primarily on OpenCV, which is a Python library that allows us to manipulate our images to detect contours, points, as well as colors. So for example, because we chose to fly the Transifine autonomously, we needed a way to keep our robot centered. To do this, we masked the camera feed to isolate the blue color of the inner 2 lines, then used the endpoints of the lines as coordinates to calculate the vector that would determine our ROV's required motion. By calculating these values using an updated camera feed, as well as continuously sending these values to the thrusters, we can ensure that the robot would not drift too far to the side and remain moving straight ahead. I'll now pass it on to Alex to talk a little bit about 3D modeling.
So for 3D modeling, for 3D modeling this year, we chose to use a program called Regard 3D to model the coral head. However, Regard 3D requires that we have a large and high quality photo data set. So we created a nav system that allows the robot to travel in 360 degree motion around the coral head in order to get photos of the coral head from all 360 degrees. And then further, to measure the diameter and the height of the coral head, we employed the use of these these lasers here. And the lasers are placed precisely 5 centimeters apart. And what this allows us to do is it allows us to get a pixel to centimeter ratio in the camera frame, allowing us to measure anything in the camera frame. Finally, all we do is we display the model and the dimensions together in order to complete the task. Now I'll be passing it to Martin to talk about the GUI.
With all these programs, we implemented a GUI, which is also commonly known as a graphic user interface. This graphic user interface, or also GUI, uses Python libraries like OpenCV, multi-processing, as well as Pygame. The one library that is most important to us is multi-processing, because this allowed us to run multiple programs, as well as our autonomous programs, and our thruster controls, lasers, anything, you name it, all at once without overloading our terminal. And I'll be now passing it to Zen, and I'll now be passing it to the float engineers.
So yeah, at the beginning of the year, our float had a structure of 2 cylindrical containers, and after painstakingly piecing that together, we realized that waterproofing that float was not something that we should commit to. So we had to redirect our focus, and eventually we landed upon using a plastic box to act as our main structure. Now, with the plastic box, it allows for an easier fabrication process without having to sacrifice much functionality. And by much, I mean no functionality at all. So for the internal buoyancy system, we have a linear actuator that is controlled by an Arduino, and externally there is a syringe that is connected to that linear actuator. On the tip of the linear actuator's rod, there is a 3D printed piece that connects to the rubber plunger for the syringe, as you can see here. And that allows for essentially like a hand controlling the plunger. So to give you a little bit more of an image of what the process would look like, at the beginning of the float cycle, it is at the top of the pool where the syringe plunger is all the way down. And then once it reaches a certain time point, the Arduino signals to the linear actuator to start pulling the water from the pool into the syringe. Once that is done, the float becomes negatively buoyant, thus sinking down until it reaches the bottom of the pool. Once it reaches the bottom of the pool, the Arduino signals to the linear actuator to push that water out from the syringe into the pool, and thus making it positively buoyant, making the float ascend to the surface and thus completing a cycle. And aside from technical experiences, we also learned various management skills, and most importantly, the prioritization of ease of use with fabrication. Originally, our design had the 2 cylindrical containers like I mentioned, and those were fastened together with flex tape, and that did not allow for a very seamless transition from testing to troubleshooting. But with this new design, there is a latch that opens and closes the float, allowing for a more seamless transition. And I'll pass it on to Hannah for more information.
Yeah, so to power the float, we use 8 1.5-volt non-rechargeable AA batteries, and specifically the batteries power the linear actuator, the H-bridge motor driver, and the Arduino. And then the linear actuator is controlled by a simple H-bridge Arduino circuit. And then for the data transmission aspect, we use a ESP32 LoRa system. And if you have any questions about that, we can definitely answer that. But I guess I just have.
Awesome. And that concludes our engineering presentation. Judges, if you have any questions, we'd be happy to answer them now.
So you use the LoRa system for communications? Yeah. All right. I don't think I've heard of anyone else doing that.
Oh, yeah, no, I just wanted to move the frame so it's not resting on the claw.
Yeah, I noticed that.
It's a robust clock.